Okay, so this is a two-presenter presentation. I'm going to do about the first two-thirds, and then Andy's going to do the final third. First thing I want to say is a bit about where these fossils come from, because the sense I get in the UK is that from most people, a goodly number, fossils are things you find in museum cabinets, but they actually come from the ground and rocks, and it determines what you get and how you get it. So I want to say a bit about these fossils that we get from the Centrosaurian fossils we get from Dinosaur Park. I also need to give you a sense of geography and scale. Again, most people in Western Europe and the UK don't appreciate the size of Alberta. It's just one of the Canadian provinces. There's the British Isles for scale. And so the lower half of Alberta is basically late Cretaceous rock, and the upper half is early Cretaceous. And so we've got loads of potential fossil-bearing material, but we haven't even got 4.5 million people. So we haven't got the density of eyes finding fossils for us. And also the northern half is unfortunately covered by an awful lot of forest. Anyway, I want to mention, can come to geography. Here's the Royal Tyrrell Museum, and that's Dinosaur Provincial Park. It's about an hour and 45-minute drive away. For political reasons, the museum wasn't put near Dinosaur Provincial Park. And so satellite view, there's an awful lot of outcrop. It's an extremely arid area. Alberta lies in the rain shadow formed by the Rocky Mountains. And you can see in this picture here, I think this is, and that area there, that's where it's brown and gray, that's just bare rock. The rocks aren't that well lithified, and they're eroding extremely quickly. And the map there on the right shows you the extent of the park. You can just see the dashed red outlines. So it's about 80 square kilometers, but it's produced 350 complete skeletons, many tens of partial skeletons, and tens of thousands of isolated bone. There's places in the park you just walk over it with your boots. It's just rubbish bone. Anywhere else in the world you'd worship it, but with us it's just shoulder stone. The park records three different types of environment in three formations. At the bottom, you've got the Old Man Formation, named after the Old Man River. The main part is the Dinosaur Park Formation. These paintings were commissioned by our geologist, Dave Eberth, based on his interpretations of the environments. And at the very top, the last few meters, you've got the Bear Paw. It's part of the Western Interior Seaway. It's a fully marine conditions. And there's a stratigraphy done. It's about 120 meters thick. It spans about 2 million years. So the Old Man Formation, the conditions were not good for the preservation of dinosaurs. We know they were there. We've got a few skeletons and a few isolated bones. But it's not till you come to the Dinosaur Park Formation, and that's where the Centrosaurus material comes from. We've got the hundreds of complete skeletons and thousands of bones. And it's not just dinosaurs. We've got frogs and fishes and birds. Plants are actually quite rare. But it's the large-bodied dinosaurs which tend to be preserved the most. And the Bear Paw Formation, in the immediate area of the park, we don't get much, but elsewhere in the Bear Paw, we actually get dinosaurs that were washed out to sea. We got 2 this year, 2 hadrosaurs. But we've got many tens of marine reptiles. We've got mainly about 4 different types of mosasaur. We get turtles and fish and stuff. But that's not so much near the park. When you're there, I mentioned it's a very arid area. It looks quite desert-like. The 3 hazards in the park are cactus, rattlesnakes, and scorpions. It sounds like the American Southwest. But those animals have to put up with minus 40 in the winter. And you can already see that there's a mix of rock types. It's mainly sandstones, siltstones, and mudstones, and there's no real pattern. The bottom part of the park tends to be more sandy, and when you get the upper half, it's more mudstone rich. And towards the very top, you start to see the influence of the seaway coming in. So I was there in the park for 2 weeks this summer. Some of you might know Jeremy Martin there. Him and I were there looking for sampling dinosaur teeth because he wanted to do a calcium isotope analysis on the teeth. Our collections are full of teeth collected decades ago, but there was no stratigraphic position, so we wanted to be more precise with GPS. I like this picture because it shows the two main rock types that we get dinosaur fossils from. We have the overbank mudstones and we have the channel sandstones. And that's important for the story that Andy and I are presenting today. So I've these aren't from Dinosaur Park. I just grabbed these off the internet for typical sandstones and mudstones. So it's the grain-on-grain contact in a coarse sandstone. The quartz mineral is actually strong enough to resist compaction. But in contrast, the smaller quartz grains in a mudstone and a mix of finer mineral material, it's not, and it actually behaves in a ductile fashion. And that really affects the fossils. So this is what the sort of data we've been working with. Andy, I hope, is going to say some more about how we get these meshes. So because I'm deep down, I'm really a maths and physics type, masquerading as a paleontologist. These were the sorts of models we got based on material in the museum or elsewhere. And in a strong, rigid sandstone, the skulls are almost pristine. But in the weak, ductile mudstones, it's when you start to see this extreme deformation. And so we've got a whole range of skulls from very nice. This is this specimen on the left here. Yeah, your left. It's now in the American Museum of Natural History, but it came from Dinosaur Provincial Park. And the other one is one we have in our collections. And Andy put it to me, knowing that I could manipulate three-dimensional objects. What would it take to restore this back? And that question Andy has, and Dave Hone, his supervisor, is, do we have just one species, or are there many species? We're looking at about 2 million years of time. Could we detect that? But you have to have reliable, consistent material to work with. So I have a really nice software system. I started using it when I was at Bristol, and I know it pretty well now. The learning curve was awfully flat for first 2 years, and then I finally mastered it. And now I've got some facility with it, and so I can do things. So let's take this original skull, and I think the first thing you notice, it's severely flattened. Fortunately, this thing died, or the skull came to rest parallel to bedding. And so the dominant deformation was compression. So these things have not experienced any tectonic deformation. It's purely related to burial. So the first thing I did, I assumed, partly incorrectly, I said, let's assume the original orbit was circular. And when you looked on the squashed one, it'd been quite flattened. So I said, let's undo that. So I multiplied the vertical component, the y component, by this factor of 1.69 to lift it up. But then when you look at it from the front, it's still not quite right. So I also assumed when I'm doing this that the bone has not changed volume. The phrase would be the bone volume is conserved. So if you squeeze it, if you stretch it in one direction, you need to bring it in the other direction so you're not adding matter and not losing matter. So then I realized maybe I should give it a squeeze by the inverse of that 1.69. Next stage, if you looked at the front, it's still a bit sheared off to the side, but I wanted to reset the skull table horizontal, so I rotated it by 6 degrees around the long axis. And then I applied another shearing motion to that to try and bring it back to symmetry. So how did we do? Here's the mangled one, and here's the allegedly pristine one, what we're assuming. And then here's the squeezed, stretched, and rotated form. The first thing, the front of the face looks not too bad, but the big difference is the frill. It hasn't been lifted up. So those transformations I applied, I did them uniformly to the whole skull. I didn't try and regionalize any of that. Our interpretation is that the front of the face, it's much more filled with much more bone, it's much more rigid, stronger, and it didn't experience the same amount of compression that the thinner parietal squamosal frill did. So this was just our first pass at doing this. Supposedly he's got hundreds he would like to have done. I don't know if we'll get to that. But we think we've got a method here for undoing stuff, and I can squeeze and shear and unmangle these things in all sorts of directions. I guess the biggest problem with this is there's no real unique solution about what stages of processing and transformation you apply. And also, if you did a squeeze, a shear, and a rotate, that's not the same as doing a rotate, a shear, and a squeeze. It depends on the sequence you apply and not just the magnitudes. The mathematician in me would want to tell you that these things are non-commutative and non-associative operators, but we'll pass. So you might want to know, how did we capture these shapes? And so that's what Mr. Knapp's going to tell you about. And we need to do this. You better do that clip.
Yeah. Cheers. Thank you. So my interest is in ceratopsian morphology, and no, that's the wrong way. So I'm applying 3D morphometrics to these fossils, which we have quite a number of, particularly Centrosaurus and Protoceratops and so on. And so I've been digitizing these using photogrammetry, and a lot of you will be familiar with photogrammetry. I've seen some really good examples at this symposium. And building 3D models allows me to landmark these in 3 dimensions. And then I can do analyses comparing different shapes of different species. And here is an example of one such analysis. This is just looking at the parietal, which is the central section of the frill in ceratopsians. And you can see that there are 3 rather lovely polygon convex holes which surround these 3 groups. And that's not an accident. These are 3 major subfamilies. So we've got the, Centrosaurines here, Chasmosaurines, and that's Protoceratops. And there are 55 specimens here. Again, this is just an exploratory, very basic analysis. But when we divide them up according to species rather than the broader subfamily, it's not quite so clear. So we get quite a lot more overlap. And one of the questions is, what is this variation? It's one of the things I'm interested in, is how do different species of ceratopsians vary in their morphologies? And the yellow, as I mentioned before, is Protoceratops, which we have a large number of specimens of different ontogenetic stages. And we know that the frill changes shape during ontogeny, so that could be a possible explanation. But then we have Centrosaurus, which is here in blue. That has quite a wide spread as well. And Centrosaurus is mainly known from the larger skulls. And I've got 15 models here of complete and fairly complete skulls. And I took these and did a much more comprehensive landmarking analysis. So this is looking at the entire skull rather than just the parietal. And here I've plotted them on a PCA. And you can see that there does look like there's a pattern of increasing squishedness moving along principal component 1 here. And 2 things to note here is that the more pristine, unsquashed skulls cluster in this region of the morphospace, but the mean shape is being dragged over towards the more flattened skulls. So if we're doing a between species comparison of morphology, this is going to be a bit problematic. But I can go one stage further than this and look at what the actual deformation looks like. So here is the same plot with hypothetical, well, not hypothetical, but shapes based on the principal component values. So here, principal component 1 is 45% of the shape variation, and you can see that that corresponds with a dorsoventral flattening, which is quite common in dinosaur park fossils. And then principal component 2 is 14% of shape variation, and that's more of an oblique strain, and that can lead to asymmetric deformation, which this is an example of here. This is CMN 348, which is very laterally sheared. Most retrodeformation techniques I've seen deal with restoring symmetry, but with these specimens at least, that kind of deformation is only 14% of the total shape variation due in this fossil assemblage. One other thing to take home from this is that horn shape looks like it's correlated with deformation, but that's actually a natural biological variation we see in centrosaurs. And we know this from multiple isolated horn cores, individual skulls, and we see this in deformed and non-deformed specimens as well. So this is the kind of thing I'm looking at and the kind of problems I want to overcome with retro-deformation, and that just leaves me to thank, in particular, these people and numerous people, too numerous to mention, at these institutions who have provided me with a great deal of help in this. So thank you very much.